Hello everyone, welcome to MEE1008 Dynamic System 1. So my name is Dr. Zahurullah. I'm the module coordinator for MEE1008 and my office is in Ashby Building, room 318, and my email address is given here. So today we will be discussing introduction to dynamics and then this specific topic, which is about kinematics of particles, including rectilinear motion and curvilinear motion. So before going into the topic, I would just briefly describe the content of this module. So as you know that the dynamic system 1, which is MEE1008, consists of two parts, mechanical part and electrical part. So I will be teaching the mechanical part, and then as you can see the module assessment. So the module assessment is again 50% mechanical and 50% electrical. Now the mechanical part is further divided into two parts. So one is the class test, which will be 10%, and the class test will be in week 18 of this semester. And the exact date for the class test is given here, and the class test will be at 9 a.m. This will be online test. So you will be provided with the question paper online, and then you will need to do the test, and then you need to upload the your solution uh, to the canvas. And there will be a written exam at the end of the semester, which will contribute 40% to the module. And the electrical part, as you know, that it's consists of again 50%, and then it can be split into 20% lab, and then you have a class test which is 10%, and then the written examination will be 20% for the electrical part. So as you can see on this slide, there is some recommended books that we will follow for the mechanical part of this module. So the first book, as you can see here, is Engineering Mechanics Dynamics by G.L. Merriam. The second book, which is Engineering Mechanics Dynamics by R.C. Hebler. And the third book is University Physics with Modern Physics by Hughes and Young. So as you see these books, you can find these books in the library. Even some of the books are available as online books, so you will be able to see them as a reference books, and also we will solve some examples from these books, so it will be a good idea to have these books with you. Now for the mechanical part, the module content, as you're going to see here. So this is the week by week topics that we will cover for this module in the mechanical part. So today is our lecture 1, and it's a week 15, and today is 22 January 21. So today we will discuss about introduction to dynamics and kinematics. And then, as you can see, I will not go into the detail, but then during the next weeks, we will discuss these different topics. The important point is that in week 4 of this semester, which is week 18, and the exact date is given here, which is 12th of February. We will have a class test, which I discussed earlier, and the class test will be in the contents covered in week 15, 16, and 17. So the class test will be in these in the content which we will cover in these 3 weeks, which is introduction to dynamics, and then kinematics, kinetics, and then work and energy. So the class test will be in these 3 topics, and the class test will contribute 10% to your module marks. Okay, so in today lecture, we will mainly discuss about the engineering dynamics. And then the difference between the kinematics and kinetics, and then about the Newton's three laws of motion, which are the base of engineering dynamics. And then we will discuss the most simple type of motion, which is what we call is rectilinear motion. And we will discuss about the displacement, velocity, and acceleration. Similarly, we will then try to discuss curvilinear motion. And again, we will discuss about the displacement, velocity, and acceleration. So in the curvilinear motion, then we will also discuss the rectangular coordinate system and the projectile motion. So as you can see on this slide here, that we have engineering mechanics, and the engineering mechanics can be split into two parts. One is statics and one is dynamics. So you may already be familiar with the statics. So you studied mechanics of material, which is part of the statics. And then you have dynamics, so which is this module. And then dynamics can be split into two branches. One is kinematics, one is kinetics. And then kinematics can be split into two branches. One is what we call is kinematics of particles, and another is kinematics of rigid bodies. So in first year, you will discuss only kinematics of particles only. And then in the second year dynamics, you will discuss about the kinematics of rigid bodies. Similarly, we will discuss about kinetics, but we will just concentrate on the kinetics of the kinetics of particles. In second year, obviously, then you will discuss about the kinetics of rigid bodies. Now, as you can see here, that now we can try to differentiate between kinematics and kinetics. So the kinematics is the study of motion without reference to the forces which cause that motion. So assume that a body is moving on the road, for example, a car. So in kinematics, we will only concern about the velocity, acceleration, and displacement of the car. So that is the kinematics. But in kinetics, it's relate the action of forces on bodies to the resulting motion. So in kinetics, then we will also discuss about the forces and the motion together. We will discuss these in further details that you will see in a coming lectures. So just to give you an idea of the Newton laws, I'm sure most of you will already be familiar with these laws. So the law one is a particle remain at rest or continue to move with uniform velocity in a straight line with a constant speed if there is no unbalanced force acting on it. The second law is the acceleration of a particle is proportional to the resultant force acting on it and is in the direction of the force. Now mathematically we can write the Newton's second law is F equal to ma, and we know that F is a vector. So normally if you try to write the vector, so in the books they normally use a bold letter, but here we will use F with a arrow on the top of it, so to show that this is a vector. And mass is a scalar, but a is also a vector, so we will also write arrow on top of it. And finally we can discuss Newton third law of motion. So the third law is that the forces of action and reaction between interacting bodies are equal in magnitude, opposite in direction, and collinear. So this is the third law of motion. Okay, so now we can discuss about the most simple type of motion, which is what we call is a rectilinear motion. So if you consider a particle, and assume that a particle is moving on this line here, and the particle is here at the particle is P, and this is the location of the particle. Now you want to show the displacement of this particle. You will measure this with some reference, and in this case we are taking this reference is O, and then this vector is what we can say is this is our S. So if you read this statement, so consider a particle P moving along a straight line, which is this particle, and moving along this line here. Now the position of P at any instant of time t can be specified by its distance S measured from some convenient reference point O. So from this point here, fix on the line at any point P plus delta t, the particle has moved to P dash. Now the particle will move to this point here, and this is our P dash point. And now the distance between P and P dash is delta S, and we know that this is our positive S direction and this is our negative S direction. Now the change in the position coordinate during the interval delta t is called the displacement delta S of the particle. So now when the particle move from point P to P dash, this delta S is what we call is the displacement of the particle. Now the displacement would be negative if the particle move in the negative S direction. If the particle is moving in this negative S direction, so then the displacement will be negative. Now we can define velocity here. So velocity is that the average velocity of the particle during the interval delta t. So we know that the particle take time delta t when it move from point P to point P dash. So this time is delta t, and the displacement here is delta S. So now the average velocity of the particle during the interval delta t is the displacement divided by the time interval, or this equation here. So this is our average velocity. So if you divide this delta S by delta t, so this will provide you with the average velocity. And now if delta t becomes smaller and approaches zero in the limit, the average velocity approach the instantaneous velocity of the particle. So now we can define the instantaneous velocity, which is so we know that velocity, the instantaneous velocity is the delta S divided by delta t, which was the average velocity. So now when delta t approaches zero, so what we can write is that limit, and when delta t approaches zero, so this is what we call is the instantaneous velocity. Now we know that this is the definition of the derivative. So this means that velocity, the instantaneous velocity, is equal to ds by dt, or you can also write this s dot. So s dot means it is the derivative with respect to time. So now you can say that that's the velocity is the time rate of change of the position coordinate s, which is this equation here, and the velocity is positive or negative depending on whether the corresponding displacement is positive or negative. Now if you know the velocity, you can also now define the acceleration. So now the average acceleration of the particle during the interval delta t is the change in its velocity divided by the time interval. So if you divide the delta v, so for example, if again you assume the same motion of the particle P here, and the particle at this location here, p dash. Now if the average velocity here is the velocity here is v1 and the velocity here is v2, the change in velocity is delta v and the change in time is delta t. So then if you divide delta v divided by delta t, this will be our average acceleration. And as delta t becomes smaller and approaches zero in the limit, the average acceleration approaches the instantaneous acceleration of the particle, and which you can write. So the instantaneous acceleration, which you can represent by a, and which will be limit, and when delta t approaches zero, and the average acceleration, which is delta v divided by delta t. So this means that a is equal to, and this equation here, so limit when delta t approaches zero, when delta t approaches zero, so then this equation become simple a derivative. So this means that it's dv by dt. And similar to this equation, we can also write this was ds by dt was s dot, so dv by dt will be a v dot. Now we can also write a is dv by dt, and now we know that this v is ds by dt. So now in this case we just replace v by ds by dt. This become the second derivative of the displacement. So you can write this is a d square s divided by dt square, and we can write this s double dot. So s double dot means that it's the second derivative of the displacement with respect to time. Okay, so now the acceleration is positive or negative. It's depending on whether the velocity is increasing or decreasing. So note that the acceleration would be positive if the particle had a negative velocity which has become less negative. So this means that if the particle initial velocity is minus 20 and then become minus 10, so then this means that uh, it's a positive acceleration. So if the particle is slowing down, so this means that if the initial velocity is, for example, 30 and the final velocity is 10, so then we can say that the particle is decelerating here. And now again, this is very important point, so that the displacement, velocity and accelerations are vector quantities. Okay, now if we eliminate dt from this equation and this equation here, because it's v is equal to ds by dt and this is a is equal to dv by dt. So if we eliminate dt from this equation, so the first equation will become v dt. So the first equation will become dt, which is ds by v, and the second equation, which is this equation here, it will become dt, which is dv by a. So you have two equations here and both are equal to dt. So if you just equate these two right hand sides, so this means that ds by v equal to dv divided by a. You can write that a ds equal to v dv. Now again, this is important equation, and you can also write this equation is s double dot, which is a is s double dot, which we the second derivative of the displacement into ds, and on the right hand side again what we can write is that velocity is s dot and then dv, so v is again s dot. So again, this equation is important. So sometime you will use this equation to solve numerical examples. Okay, so now again, if you consider a specific case of rectilinear motion when the acceleration is constant. So with constant acceleration a, and assume at the beginning of the interval, that is, if you consider this thing here, that if a particle is initially here and then it's here, so here the time is 0, velocity is v naught, and the displacement is s naught here, and a is constant, and the final velocity is v, the final distance is s, or displacement is s, and the time is t here. Okay, so when t is equal to 0, then s is equal to s naught, v is equal to v naught, and then when t is equal to t, so even you can write this t equal to t, then velocity is v, and the displacement is s here. So now if we have a constant acceleration, so then we can derive some expressions here which will make or will provide us with simple equations. So the first thing, if you start with this equation here, that a equal to dv by dt, so we know that this is one of the equation, that that acceleration is equal to the rate of change of velocity, or this is our v dot. So if you just write this equation in this form, that dv is equal to a dt, so this means that you just move this dt to the left hand side and just write this equation here. And if you look at this specific case here, and we now want to make sure that the acceleration is constant, so if we take this specific case of a constant acceleration, and now if we do the integration here, so we know that here the initial velocity was v naught and the final velocity was v, and here we have we are integrating with respect to time, so we will put the limit of time. So the initial time is 0 and the final time is t here. So you can simplify this equation. So on the left hand side you will get v minus v naught. So if you integrate this, you will get v, and if you just put the limit of integration, so which will be v minus v naught on this hand side, because we are taking a is constant, so if a is constant you can take it out of the integration, so it will be just 1, and then integration of 1 with respect to time is t, and if you just put the limit of integration, it will become a and t minus 0. So here you can derive an equation, that is v is equal to v naught plus a t. So we derive this very important equation, and this equation is only valid when the acceleration is constant, because as you can see that we take the acceleration out of the integration, and you can do this only if the acceleration is constant. So you will apply this equation in the case when the acceleration is constant. When the acceleration is not constant, then you will be just using this equation. Now again, we derived this equation on the previous slide, that v dv is equal to a ds. So if you take this equation here and again you integrate both sides, so the left hand side is you are integrating with respect to dv, and the right hand side you are integrating with respect to s. So if you just integrate this, so on the left hand side you will put the limits of velocity, which is v naught, and in v, so this means that the velocity is changing from v naught to v here, and again a is constant. The limit of displacement is s naught to s. So again we are using these equations here. Now if you again do the integration here for the left hand side, so it's v with respect to v, so you will get v square divided by 2, and you put the limit of the integration, which is v naught divided by v. And on the other hand side, on the right hand side, you have a, which is constant, and you will have s, which is s naught into s. And you can further simplify this equation. So you will say that it's v square minus v naught square. We just putting the limits of integration, so the upper limit minus lower limit. And on the right hand side, what you have is a s minus s naught. So again you can simplify this equation, that v square is equal to v naught square and plus 2a s minus s naught. So again, this is another equation that we derived from here. So the first equation was the final velocity is equal to the initial velocity plus a times t. The second equation is the final velocity square minus equal to the initial velocity square plus 2a into the final displacement minus the initial displacement. And finally, we can use this equation here, that is velocity is equal to ds by dt, which is obviously s dot. So if you take this equation in this form here, so this will be s naught and this will be s, and the so the you just putting here the limit of the displacement, which is s naught to s, and here you are putting the limits for the time, which is from 0 to t. Okay, now here we have velocity here, the final velocity, which is obviously not constant with respect to time. A is constant, velocity is not constant. So if a is constant, then the velocity will change. So we need to know now the velocity is a function of time, which we can calculate from this equation here. So if you just put the values here, so on the left hand side, what you can see is s minus s0. And on the right hand side, what you will have is that 0 to t. And you can just put this value for the which is v naught plus a t into dt. So if you do this integration here, so the integration v naught is now constant. So the first it will become v naught t, and this will become plus a t square by 2. So this means that we can write this is s is equal to s naught plus v naught t plus half a t square. So this is our third equation. So these three equations are important, but the only thing that we need to know is that these are only applicable when the acceleration is constant. So the final equation is that the displacement is equal to the displacement at t equal to 0 plus v naught t plus half a t square.